Hi, my name is Kobus Vanemeyer. I am a professor in the School of Computing at the University of Utah. I'm also the director for the Powder platform, which is a mobile and wireless research facility sponsored by the National Science Foundation that we are building in Salt Lake City, Utah. I'm delighted to tell you a little bit more about Powder and also specifically about OAI related things that we're doing on Powder. This is a cartoon picture of the Powder architecture. So we have these stationary radios. So think of these as rooftop nodes, or we are also in the process of deploying small cells that will be more in smart lampposts or on traffic signs, things like that. We have a private front haul infrastructure going to an edge compute facility. And from there, we also go to a larger metro cloud facility in the form of the Cloud Lab infrastructure. We have a small controlled RF environment that is federated with this whole setup. In terms of endpoints, we have what we call fixed endpoints. These are human height radios attached to the side of buildings. We have a number of nodes on campus buses by now. And we also have portable units that you can either put in a vehicle to drive around or carry around on campus. And we are also planning to do deploy some sensors in the Powder infrastructure. This is what our footprint looks like. So largely deployed on the University of Utah campus. The snowflakes represent some of these rooftop nodes. The blue nodes are our fixed endpoints. The green triangle here is where we will be deploying our dense deployment. In terms of compute clusters, we have a near-edge compute cluster that is connected through this front haul fiber infrastructure and running CWDM over that to the rooftop nodes. We have a slightly larger compute cluster on campus, and then an even larger compute cluster in the University of Utah downtown data center, and this is where the Cloud Lab facility is. This is a live map. If you go there, you can see our current deployment, and there are also options to show the bus routes and show the buses moving around, and if they have a little green circle around them, like this one, then it means it has one of our radios on them. So this whole infrastructure is software-defined end-to-end, and that is really a critical capability for a testbed like ours to enable a broad range of research. Of course, we recognize that not everyone will be interested in using the hardware that we have, and so we have this bring your own device capability throughout this whole architecture. And you can also think of this as bring your own software. Again, this is an open platform. We provide software building blocks that I'll be talking about in a second, but you can of course bring your own software or take the software that we provide if it's open source and modify that for your experimentation. A little bit about the experimental process. So we're not running a service all the time. We have this platform, it's just sitting there. Not doing anything until users come in, they access our control framework, they select a profile typically. So a profile is a recipe that says the resource of the hardware resource that you want, the software resource you want, the way you want that to be configured. So we provide some of those profiles, our users create profiles themselves, and that's typically the way that you start off the process of an experiment. You select a profile, the control framework takes that profile, instantiate the software, configures the hardware, instantiate the software on it, and then we kind of get out of the way. So we try to provide real low-level access for our experimenters. There's a picture of the general purpose base station. So the rooftop nodes, we have 4 NI SDRs in there, RF front end, 2 antennas. The purple stuff is out-of-band access and operations and management kind of equipment. That shows the CWDM MUX DMUX that goes to that near edge compute facility. Photos of some of the rooftop deployments. We are partnering with the Renew team at Rice University for our massive MIMO. Equipment is coming from a company called Skylark Wireless that was spun off out of Rice University. This provides us with a software-defined massive MIMO base station. So again, highly configurable, and it also gets coupled with a compute cluster to form the complete massive MIMO base station. So photos of one of the nodes deployed on one of our rooftops. This is what one of these blades look like inside. We also have one deployed currently in an anechoic chamber for some detailed measurements. This is what the patch antennas look like. This is a close-up view of one of these SDR dual transceiver nodes that go into the blades. The endpoints, both the fixed endpoints and the mobile endpoints, have this general architecture. So again, software-defined radios, RF front-end antennas. In this case, we can also take off-the-shelf UEs or SDRs associated with massive MIMO. For the endpoints, we have a co-located compute node, and again, green is experimental, purple is out-of-band access and control and management. In some photos, on the bottom left here, this is what one of the fixed endpoints look like. This is one of the bus nodes look like, and this is what it looks like before it gets deployed. And it's just a picture of some of the early experimentation that we've done with a mobile node. We have an FDD front end deployed right now, working on a TDD front end for band 41 and CBRS that we hope will be coming online pretty soon. So we're fully operational. We have 9 rooftop nodes. We will have 3 massive MIMO nodes on rooftops right now. One of them is, like I said before, in an anechoic chamber. One is on a rooftop and the other one is to be deployed soon. We have probably about 20 mobile endpoints by now. We have portable endpoints. The rest of the infrastructure is all there. And yeah, we hope to break ground on the dense deployment any day now. So our general approach in terms of domain software is that we track and replicate the open source efforts, 4G and 5G specifically. We try to stabilize the code, fix bugs if we find any, and then make that available on Powder. We typically go through this, testing it on replication of the test benches, testing it in controlled RF environment, testing it in an indoor over-the-air environment, and then eventually deploying it at scale outside. And all of these facilities are available to our users remotely. When we do research, we typically also make that available as open source and as profiles. So some of the specific stacks that we have available as click-through profiles, so it's, building blocks that you can really easily instantiate. SRS RAN for FDD, for TDD, we're combining SRS RAN with OAI. Real interest in the 5G stacks, and right now OAI in terms of the RAN is really the stack out there. There's also work from Open5GS and the UE Ransom folks, and we have a profile that combine these two for more of an emulated 5G environment. The Renew folks are providing us with software for our massive MIMO deployment. So there's a Renew lab that is available that is non-real-time toolkit. We expect to get a real-time baseband implementation real soon, and they're also working on MAC layer implementation. Other sort of related stacks, ORAN, we have combined the ORAN Alliance software stack with both OAI and SRS RAN. I'll say a little bit more about that in a second. We also have other sort of supporting stacks available around network orchestration and management, so ONAP or containers, think Kubernetes, or cloud, think OpenStack, and of course, RF monitoring, tools like a new radio. And then we provide a whole bunch of platform-specific tools to enable users to do experiments on Powder. So a little bit more on OAI. Like I said before, we basically try to track what the OAI is doing and then try to build it out at scale. So in terms of non-standalone, we've been testing with the configuration that they have. So COTS UEs, OAI eNode B, OAI EPC, OAI GNode B. And most of our testing has been trying to figure out what COTS UEs we can make use of in our larger deployment. So we've been testing all of these, and the ones in italics are the ones that we had most success with. And most likely we'll probably try to deploy either the QuickTel or the SIMCOM module at scale. So yeah, that's the plan. And then in terms of 5G standalone, again, this is what the OAI workbench looked like. So we have replicated that here, and we have 3 of those setups. Again, they're remotely accessible by our users, and is doing SDR-based UE and then GNodeB. We also are testing with the same set of COTS UEs for standalone, and hopefully we'll be able to use the same COTS UEs for both standalone and non-standalone. And again, plan to deploy this at scale in our different over-the-air environments. To wrap up, yeah, like I said, we have worked with the OpenStack code bases that have both SRS LTE or SRS RAN, as they're now called, and OAI, and trying to combine that with the software stack from the ORAN Alliance. So we have built an E2 agent that speaks to the RIC over the E2 AP transport. We support the ORAN defined service models. We made use of the ORAN RIC bronze release. Yeah, we have the basic agent implemented. We have the E2 AP and E2 SM implemented. And this again available as a Docker profile. The RIC is available as a Docker profile, and then also OAI eNodeB interconnecting with the RIC. Thank you very much.